Okay, so in this video I'd like to talk about the prime product formula. Okay, so the prime product formula, and we'll come back to the equation in a second, it was discovered by Leonhard Euler in 1737 at the St. Petersburg Academy, and this is in St. Petersburg, Russia. Okay, so Euler was the one who was able to find this equation, and he started with this 1 plus 1 over 2 to the s. Oh, and I should note, s here is going to be a variable, okay? So it can take on any value. But for now, we'll just leave it as s. So he started with this series, this sum of infinitely many terms, right, of 1 plus 1 over 2 to the s, plus 1 over 3 to the s, plus 1 over 4 to the s. You can see here we have all of the integers. Okay, and then Euler was able to find that this equals this long infinite product. Okay, so product just means multiply. So all of these terms, okay, I would, if you're not familiar with term, this would be a term, and this would be a term, or this is another term, or this is another term. So like each individual piece. Okay, so Euler was able to see that this infinite sum is equal to this infinite product with prime numbers in it. And to my knowledge, this is the first equation that we found that has all of the primes in it. Okay, so 2, 3, 5, 7, 11. Okay, so Euler was able to find this, and we call this the zeta function. Okay, today we do. And it's got this nice symbol here. This is the zeta symbol. It's kind of like an S with a curl on top. Okay. So, in this video, I would like to show to you how Euler took this infinite sum here, okay, and how he was able to find that this sum is equal to this product. So, if we have the sum 1 over 1 plus 1 over 2 to the s plus 1 over 3 to the s plus 1 over 4 to the s, and that just keeps going forever. Okay, and we're going to just call this the zeta function. Okay, so here I could put in any number I choose. Like, so let me give you an example. Zeta of 2 would be equal to 1 plus 1/4 plus 1/9 plus 1/16, and so on. So Euler was actually able to find that this is equal to pi squared divided by 6, pi being the circle constant. Okay, so that's the general idea. So we start with the zeta function, and what Euler did is he multiplies the entire zeta function, we'll just call it zeta of s, so this huge string here of different terms we're adding up to infinity. We're going to multiply the entire thing by 1 over 2 to the s, okay, by essentially this term right here. So, what would that give us? Let's change colors. So, 1 times 1 over 2 to the s would just be 1 over 2 to the s. This term, 1 over 2 to the s times 1 over 2 to the s would just be 1 over 4 to the s, plus, here we have 1 over 3 to the s times 1 over 2 to the s. That's 1 over 6 to the s plus, and I think you could see the pattern, 1 over 2 to the s times 1 over 4 to the s gives you 1 over 8 to the s, and this goes on to infinity. Okay, so the next, and this is really where Euler's great idea shows up. He's going to take this result, and he's going to subtract it from this, our original series. Okay, so let's see what that would look like. So we have the zeta function, the original zeta function, minus the zeta function multiplied by this 1 over 2 to the s. Okay, so zeta. Okay, so let's look at the series. So we have this here, this series, and we're subtracting this from it. So it's pretty simple. You don't have to worry too much about the infinity. We'll do it one at a time. So here, there is no 1 here. So this term would stay. This 1 would stay. So we've got 1, and they're all plus, so we'll just leave it as plus. So next, notice this one has a 1 over 2 to the s, and we're subtracting a 1 over 2 to the s. So this term goes away, okay? And notice that there is no 1 over 3 to the s, so this term would stay. So we have plus 1 over 3 to the s. And continuing this logic, Now, this has 1 over 4 to the s, and we're subtracting 1 over 4 to the s. We can ignore that term. And then this would be 1 over 5 to the s, which is not in this one, so we'll have that term, 1 over 5 to the s. And you may be able to see the pattern coming up. If we kept going, there would be a 6, but there's a 6 here. Then there'd be a 7, but there is no 7 here, so we had 1 over 7 to the s. And if you notice, these are all going to be odd numbers. Okay, so plus 1 over 9 to the s plus, and that goes on to infinity. Okay, so one nice, neat way we can clean this up a little bit is notice that each of these terms here have zeta of s in it. So if we factor that out, we would have zeta of s times by, well, what's left here would be 1, and what's left here would be minus 1 over 2 to the s. So that's equal to this series right here. Equal. Okay, so the next step Euler did was he has this series right here, which is this, and he's going to multiply this entire thing by 1 over 3 to the s. So let's do that down here. So 1 over 3 to the s times by this 1 minus 1 over 2 to the s times zeta of s. Okay, so if I multiplied this entire series by 1 over 3 to the s, this first term, 1 times 1 over 3 to the s, that just is 1 over 3 to the s. This second term here, 1 over 5 to the s, becomes... Oh, I'm sorry, I skipped one. The second term here, 1 over 3 to the s, becomes 1 over 9 to the s. And this term right here, 1 over 5 to the s, multiplied by 1 over 3 to the s, is equal to 1 over 15 to the s. And we keep going. Here we have 1 over 21 to the s, and next we have 1 over 27 to the s, and it goes on and on forever. Okay, so Euler's next step, and hopefully after this one you might be able to start seeing what he was doing. His next step was to take this new thing and subtract it from the old thing, okay, from this. So essentially you have this series right here, and we're going to subtract this series right here from this one. Okay, so we're going to subtract, minus. Okay, so let's see what that looks like. First we have this thing here, so zeta of s times 1 minus 1 over 2 to the s. Okay, and then, so that's this series. And we're going to subtract this new series, where we multiplied this term by 1 over 3 to the s. So that leaves 1 minus 1 over 2 to the s times the zeta of s. And so let's look at what our series would look like now. Okay, so subtract this from this. So notice this has no 1 term, so the 1 stays. So this is equal to 1, and then plus. So notice they each have 1 over 3 to the s. So this minus this would just give you nothing, so they would cancel out. And then notice there is no 1 over 5 to the s here, so this term would stay. So plus 1 over 5 to the s. Okay, and notice here, this has a 1 over 7 to the s, and this does not, so that would stay. 1 over 7 to the s, and then we have plus... These each have 1 over 9 to the s, so these would cancel. And here, remember this is just all odd numbers, this series, so it'll be easy to keep going. So the 9s cancel, and then we have 1 over 11 to the s would be our next term, and this doesn't have it, so plus 1 over 11 to the s. Okay, let me keep going. Plus, and this would have a 13, but this doesn't, so 1 over 13 to the s plus, they each have 15s. Remember, this is all odd, so this would have 15 and this has 15, so they cancel. Then this would have 17 and 19, and these don't, so we can put those in. Okay, 1 over 17 to the s plus 1 over 19 to the s. You can kind of see what's already happening. Essentially, like all the numbers that weren't prime are being subtracted off one by one. Okay, and even the primes are being subtracted off just slowly, but you'll see, so this goes on forever. So hopefully after this very next step, you'll be able to see what's happening. Okay, so this is the series we're left with, and let's clean this up a little bit, and you'll start seeing the pattern, because it'll become obvious after this one. Okay, so notice that each of these terms, they're getting big and bulky now, so it's hard to see it. But each of these terms has this zeta of s times by 1 minus 1 over 2 to the s. Okay, that. So we can factor that out. So we have zeta of s times 1 minus 1 over 2 to the s. Okay, and here I'd be left with just 1. And here I'm left with this minus 1 over 3 to the s. So minus 1 over 3 to the s. Okay, so you can probably guess what's going to come with the next step. Okay, so that is equal to this series up there. And let's look at that series one more time. Okay, so the very next step we have to take is now we're going to multiply this whole thing by, well, what would be the next logical guess is this 1 over 5 to the s. Let's eliminate all the 5's and the multiples of 5. So, multiplying this by 1 over 5 to the s times zeta of s times 1 minus 1 over 2 to the s times 1 minus 1 over 3 to the s. So this would be equal to, switch back to a green. So, if we multiply this whole series here by 1 over 5 to the s, this first term be 1 over 5 to the s plus 1 over 5 to the s times 1 over 5 to the s is just 1 over 25 to the s, plus, this would be 7 times 5 is 35, so 1 over 35 to the s, plus 1 over 11 times 5 is 55 to the s, plus, and it goes on and on forever. 13 times 5 is 65, so the next one would be 65 to the s. Okay, so now like before, once we have multiplied our original by the next prime in the series, now we're going to subtract this from this. Okay, just like we have been doing. So, let's write that out in its full glory. We have zeta of s times 1 minus 1 over 2 to the s times 1 minus 1 over 3 to the s. By the way, this is the last one I'm doing. You'll see the pattern after this. Minus, now we have this term right here, which is 1 over 5 to the s times zeta of s. Okay, next we have times 1 minus 1 over 2 to the s times 1 minus 1 over 3 to the s. Okay, so let's notice right away that this can be simplified. Okay, so let's see that each term shares this big factor. Zeta of s times 1 minus 1 over 2 to the s times 1 minus 1 over 3 to the s. So if we factor that out, we have zeta of s times 1 minus 1 over 2 to the s times 1 minus 1 over 3 to the s times, well, let's see what's left now. Once I factor this out, I'd have a 1 left here. So 1 minus, and then once I factor this out, I'd have a 1 over 5 to the s here. 1 over 5 to the s. Okay, and I hope you can see the pattern now. As we keep going, we're going to keep getting the primes looking like this. Okay, so when we actually subtract these series, remember the series, okay, it's this one up here. I'm sorry for the slantedness. Okay, so we have this one up here, and we're subtracting from it this one down here. Okay, so first we have, so we're subtracting this from this. Okay, so notice that this doesn't have a 1 in it, so we'll have a 1 to start with. So it's 1 plus, okay, and then notice that each of these have a 1 over 5 to the s, so that gets canceled. And this doesn't have a 7, or an 11, or 13, or 17, so all of these numbers continue, and the next one that gets subtracted would be this 1 over 25 to the s. Okay, so 1 plus 1 over 7 to the s plus 1 over 11 to the s plus 1 over 13 to the s plus 1 over 17 to the s plus, and it goes on and on forever. And now I think you kind of see it. Okay, so I'm going to write it out. Let's assume I continue this process to infinity. So the next time I would multiply this whole thing times by 1 over 7 to the s, and then I would subtract that from this thing. Okay, and I would just keep doing that process until I eliminate all the primes. And as you'll see, the primes are infinite, so this is an infinite process, and you can kind of imagine going to infinity in your head. Okay, so the pattern that we're going to see after we take this to infinity be zeta to the s, zeta of s, times 1 minus 1 over 2 to the s, times 1 minus 1 over 3 to the s, times 1 minus 1 over 5 to the s, times 1 minus 1 over 7 to the s, times, we're going to keep going, 1 minus 1 over 11 to the s, times, well, you can guess the next term. It's going to have a 13, then a 17, then a 19, then a 23, and all of these are going to be prime. So after we subtract everything off, if you might have noticed, the common theme that when you subtract it is that the 1 was always left behind. Okay? The 1 never got subtracted away. And it's true that when you do this process to infinity, you're going to be left with just 1. Okay? So this whole thing right here, okay, is just going to be equal to 1. So the next step Euler did is he says, okay, well, I want to get the zeta function here, the zeta, all by itself. Okay, so one way I could do that is to divide everything by zeta, and then I'd get it on the other side. But that won't be as nice looking. So what we're going to do is divide everything by everything that's not zeta. So all of this. Okay, this whole infinite product, we're going to divide both sides by that. So what you get is that the zeta function is going to be equal to 1 divided by this whole thing. 1 minus 1 over 2 to the s times 1 minus 1 over 3 to the s times 1 minus 1 over 5 to the s times 1 minus 1 over 7 to the s times 1 minus 1 over 11 to the s, and it goes on forever. Okay, and to clean this up just a little bit more, the zeta function is equal to, I can break up all of these terms in this product so that it's 1 divided by 1 minus 1 over 2 to the s times 1 divided by 1 minus 1 over 3 to the s, okay, and we can put parentheses around these, okay, times 1 divided by 1 minus 1 over 5 to the s. Okay, and you get the idea. So next, to clean it up just a little bit more, you can always multiply anything by 1, okay, and it still is the same thing. Like multiplying 2 by 1 still gives you 2, or multiplying 100 by, let's say, 55 divided by 55, notice this is just 1, is still 100, okay? So you can multiply anything by something equal to 1. So, when I take, let's say, I'm just going to take one term at a time. Okay, and I'm going to multiply this 1 over 1 minus 1 over 2 to the s. And I'm going to multiply it by 2 to the s over 2 to the s. So in the numerator, I'll be left with a 2 to the s, and the denominator, I'll have to distribute, so the 2 to the s will go into the 1. Okay, so that'd just be 2 to the s minus, and then 2 to the s times 1 over 2 to the s. The 2 to the s's will cancel, and you're left with 1. Okay, and you can imagine doing that for every single one of the terms. So like this one, I'll multiply it by 3 to the s over 3 to the s. This one would be 5 to the s over 5 to the s, and so on. So that's how I get that the zeta function is equal to 2 to the s over 2 to the s minus 1, 3 to the s over 3 to the s minus 1, 5 to the s over 5 to the s minus 1. And it goes on and on forever. So, that's how Euler discovered this. So, and why is this important? Let's go back up to the top, after all of our work, to look at the original equation and the prime product formula. Okay, so why is the prime product formula so important to us? Well, To this day, we still cannot figure out the pattern in prime numbers. Okay, we can't predict the next one. There's no formula out there that can tell us what the next prime is. Essentially, what we have to do is take all the numbers 1, 2, 3, 4, 5, 6, 7, 8. I'll give you the general idea. 9, 10, 11, 12, 13. We'll just go to 14. Okay, so I essentially I go through and I eliminate everything that's not prime. Okay, and I know 4 is not prime because 2 goes into it, so that's eliminated. 5 is prime. 6, 3 and 2 go into that, so I can eliminate that. 8 has 2 and 4, so I can eliminate that. 9 is 3 and 3. 10 is 5 and 2. 12 is 6 and 2. 14 is 7 and 2. So essentially you can see I'm eliminating everything that's not prime, and what's left are prime numbers. Okay, so you can imagine that considering there is an infinity of numbers out there, this process is infinitely long. You never stop going, and today we have supercomputers that do this for us and eliminate. And it still takes, once you get into super high numbers, it takes supercomputers a huge amount of time to even find 1 or 2 of them. So it's an inefficient process, and we've been looking for a formula for primes since we really started math. Okay, and Euclid back in 300 BC was the first to prove that primes were infinite. Okay, and since that time, most mathematicians, the best ones out there, have been looking for this formula, and nobody has found it. Okay, so that's why something like this is so intriguing, because the primes show up in this equation equal to this equation with all the integers. Okay, and so why is it even important to find the pattern in prime numbers? Well, one practical example is in cryptography. Okay, this is like code breaking, that kind of stuff. A lot of the stuff that the NSA does. And anytime that you have a financial transaction online where you use a credit card or a debit card or something like that, you probably don't know it, but they're actually using really large prime numbers to send your information across a public domain. Essentially, you have to be able to hide your information while also keeping it in plain view. So we use prime numbers and some really clever tricks to be able to carry this out. So there's actually some problems out called the Millennium Prize problems, and each of these offer $1 million, $1 million, if you can prove something in mathematics, and one of them is concerned directly with the zeta function. Okay, and I'm not going to go into the details of the exact problem, but essentially the idea is that along the way of proving the result in the zeta function is that you'll come across the pattern of prime numbers. We think that this is kind of like the key equation for primes. Okay, and that is why I wanted to show you this.